Okay, good morning to all. I can't really speak Italian, unfortunately, although I'm trying to learn it. I'll be talking about bioprotection and biocontrol. It's a very huge subject. What does biocontrol consist of in when applied to winemaking? A pretty simple definition is that it is a fight against undesirable microorganisms while by using selected microorganisms. It's nothing new. Bioprotection is something that we've created a few years back with yeast for alcoholic and for malolactic fermentation. But the biocontrol of pre-fermentation is my subject, and Professor Tonelli will also discuss a specific aspect as part of that, which is late harvest grapes for this use, or grapes for passito. There are many risks and many steps in the production. The red pointers show the points during the process where SO2 is added in order to minimize microbial risks. And before fermentation, the major risk is that connected with Cloaca apiculata, which grows pretty fast during pre-fermentation steps, and it can produce 10 times more volatile acidity compared to Saccharomyces and other yeasts. Other risks come from Brettanomyces, although it is more often found during aging. But there can be Brettanomyces infections that are hard to control. And then there are some bacterial risks, and a risk which is not really such, but that is potentially one, which is a spontaneous fermentation onset with indigenous Saccharomyces cerevisiae. So unwanted that can provide problems during a clarification of white or rosé musts with unwanted onset of alcoholic fermentation. Now, to see what these yeast can do, we chose a yeast, a Metschnikowia fructicola, to run experiments on fruit. For instance, you have apples, you have control apples inoculated with mold, and then Metschnikowia fructicola on the bottom part of the photo. The Metschnikowia fructicola really limited the development of molds, so you have a visual indication of what you can obtain using biocontrol. In winemaking, we did not use a single strain. We chose a winemaking strain working with the Burgundy and Institut Oenologique de Bourgogne. They isolated yeasts from unfermented grapes and must. The yeast had to have good growth and low temperature to be used, and a very low fermentation capacity, a very low production of acetic acid, and they had to contribute positively to the bouquet. So it's the world upside down, because it's a yeast that is selected not to ferment the wine but to avoid fermentation. This is Metschnikowia fructicola, scientifically speaking, and the trade name is Gaia. It does not have any fermentation power, or a very low one, and so it can really be used to control fermentations for specific purposes. This is an experiment carried out in Italy. This is Moscato must cold stored for some months. The objective was to have fermentation later on during the process to sell fresher wines during the summer season. And the problem was that we had to keep the must at 0 degrees. As soon as it warms up, the fermentation begins naturally, and that can have serious consequences in the production, in terms of the production of the final wine, if you can't control that process. We compared the two different tanks, the standard procedure and the other one inoculated with Gaia at 0 degrees. Now, what happened later on down the way when the muster was warmed up? As predictable, spontaneous fermentation, alcoholic fermentation started on our control, while no fermentation began during that stage in the one that had been inoculated. In the third step, we inoculated Saccharomyces cerevisiae, selected yeasts, in both tanks. At the end of the fermentation, we analyzed various readings, including acetaldehyde, and there was a lot more acetaldehyde in the wine that had fermented spontaneously, because of the flora it had developed. The apple-like flavor that results from that had developed, and also there had been a problem in controlling the sulfites because of the combining potential of acetaldehyde. Another test was run in Italy on the same microorganism. The grapes had been stored at -2°C. In this winery, there was a need to preserve the must at -2 and filter every other day until bottling to avoid spontaneous fermentation. The same process, but with inoculation of Gaia, made it possible to keep the must at 0 degrees instead of -2 and without filtrations, intermediate filtrations. And these are the results. The concentrations in sugar and alcohol and the filtration dates are shown here. What I didn't mention is that in order to inoculate with Gaia with this procedure, the must was taken to 10 degrees Celsius and then it was brought back to 0 degrees. So because of the temperature, the fermentation had just begun with very little alcohol being developed, and then it was preserved at 0 degrees. So Gaia works well at low temperatures, and it's something that you can really avoid by inoculating at 0 degrees without bringing the mustard to 15 degrees for the period I have mentioned. Another reason for interest is that there is an excellent adaptation in pre-fermentation to pre-fermentation conditions. This is a test that we ran at our lab with two samples, one inoculated with Gaia and another one inoculated with Saccharomyces cerevisiae to compare. And also we initially inoculated Clochera apiculata, and you see the during fermentation, good growth before fermentation. The population is kept during the fermentation, and then the population significantly decreases because Metschnikowia fructicola is not a microorganism that will survive for very long. So the population is kept stable throughout the pre-fermentative stage until the beginning of fermentation. Another experiment was carried out to really stretch the limits of our yeast to see if it could survive after a certain time period. Inoculation at 0 degrees and storage at 0 degrees C in Moscato for a long period. The population of Metschnikowia survived pretty well under extreme conditions.
When talking about bioprotection and control, we are interested in antimicrobial activity, especially in phenomena that develop very rapidly in cold maceration. I would like to offer you some examples. That was a Syrah Côte d'Iron with 3 different study approaches. You see the Clochera apiculata population, and sulfitation happened once only when filling the tank. Then there was a double sulfiting, but again a second one happened during cold maceration, and then there was a non-sulfating tank with inoculation of Gaia. When controlling the Clochera apiculata population, we detected a first result which was not as good vis-à-vis the double sulfating, and though it is difficult for various reasons to do the right dosing, the populations are significant anyway, even after sulfating. We also have another example coming from the States, 4 days of cold maceration. There we investigated the effects on the species of Ansenia spora ovarum and Saccharomyces as well after pre-fermentation maceration, and we see huge differences in terms of populations. We wanted to do even more than that and protect the harvest even more. And we started this experiment in Val du Loire, and we used a kit for spraying of yeasts directly applied to the harvesting machine, which means that this happens during harvesting in order to have a right homogeneity of the yeast from the very beginning. We have a sulfated and non-sulfated control too, and we obtained the very same results. So this was just to tell you about the effect and limit of SO2 in relation to microbial control. The results with Gaia were better, but we observed the same trends, that is bioprotection with Saccharomyces cerevisiae 1 gram per hectoliter. With such a low dosage, we wanted to avoid start of fermentation in the pre-fermentation period, and pre-fermentative maceration took 6 days. This is a complex graph. Please focus on the dark green color, which depicts populations after 5 days of maceration. And you see the different evolutions depending on the formulas of bioprotection. On the left-hand side, Metschnikowia, and then Saccharomyces at the center, and non-Metschnikowia and non-Saccharomyces yeasts, possibly Clochera. Each time we assessed the spraying technique with Metschnikowia and Saccharomyces too. With reference to the former, good effect in case of spraying, good survival after 5 days. Saccharomyces now, their spraying permitted a better biocontrol on the indigenous yeast rather than sulfating control, and you have a lot of Saccharomyces left if you use non-indigenous Saccharomyces. And you also have a better control than when obtained with SC at this temperature in the sulfated and unsulfated controls. I would also add that it was an early treatment, and that was definitely beneficial. We also assessed the production of compounds and the development of Clochera, which is important in relation to aromatic acidity. That was done together with IFV. You see these 4 cases, and in these 4 cases, there was a non-contaminated control, a must contaminated with Clochera from the beginning, and another one contaminated with Clochera and also Gaia. If you add Gaia, you manage to totally avoid the production of acid volatility, which we had in the non-contaminated control. So this effect of biocontrol of Gaia is, I would say, visible, tangible. And we wanted then to make a step forward, and we decided to try and change the nutritional control in order to see whether we had an effect on also MF, and that in relation to assimilable nitrogen in the pre-fermentative phases. Here we have the consumption of nitrogen in the three systems: inoculation with SC in blue, no consumption, and then the arrow tells you when there was the inoculation of SC, then another gray with which depicts inoculation with Gaia in the beginning, and then cloaca in yellow, in addition to Gaia. In the cases of Gaia inoculation, basically there is no consumption of nitrogen, 10 milligrams per liter, perhaps in pre-fermentation phases, and then there is a drop in all cases in terms of consumption of SC. So we preserved the vitamins. Very few changes have occurred, and the nutritional protocol does not change. Therefore, if you use Gaia, you apply the very same protocol for the usage of yeast as previously. Another point that needed to be checked and considered was avoiding sensorial problems which might derive from the usage of Saccharomyces yeast. A different type of Metschnikowia was used in this case. Here we have the averages, the mean values, I mean, and we see the result of sensorial activities after this approach. We don't know whether there is a direct effect. We have not analyzed metabolized in depth yet. Anyway, let's try and summarize and be practical and say that we can use Gaia directly at the harvesting machine. You spray it, and you can also use it when hand harvesting, when using the presser destemmer. If the transport time between from the vineyard to the winery, if that is not too distant, you can also move on to the maceration. And then in white and rosé wines, you can use a Gaia when filling the tanks or when sieving, and there is less SO2, so there is an oxidation risk and also microbial risk, in this case with reference to temperature. And so you have to avoid in that way fermentation during the phase of removing the lees. And indeed, we have to favor the indigenous Saccharomyces in that respect. Practically speaking, the normal dosage is 7 grams per hectoliter, and if there is a higher microbial load, you have a higher pH, or you might have a higher temperature when transporting grapes. So you have to consider the duration of transport, even though, and that goes also for conditions where the health of the berries is a source of concern. Now, before talking about the dried grapes wines, let's summarize Gaia advantages. It is excellent in terms of power of adaptation. It can be used on fresh grapes before transport or before drying, and also during the filling of the tanks for biocontrol in cold maceration or for preservation of cold must before starting FA. Alcoholic fermentation. This limits the increase in VA, and it also gives safety in terms of AF. And this also is highly compatible with the following drying techniques.